Yes. So during the last session, what we have done first is defined a directional derivative, right? And also we have defined the gradient of function of two variables, three variables, and so on. And we have seen the relation between its directional derivative and the gradient of the function of gradient of f, right? It's going to be the dot product. And then we have listed the property of uh, uh, not a property. We have listed three properties of directional derivatives. Okay, and it says that that the function will increase most rapidly in the direction of grade f. It will decrease most rapidly in the direction of minus grade f, and you will notice no change, okay, when you take any direction which is orthogonal to the grade f. Okay, right. So uh, so we have an example here. Okay, so that's what we were left, okay, in the last class. So example is you have to identify the directions in which the function f of x comma y equals to this is the definition of the function, increases most rapidly at the point 1 comma 1 and decreases most rapidly at the point this and this. So if you I have a figure of this surface f of xy equals to x square plus y square by 2. Okay, so it's going to be a circular ball. Okay, and in the xy plane it's a circular ball. Okay, so this is a circle. Now if you take any circular ball, or roughly you can also take an elliptic ball. Okay, bowl, I'm sorry, it's bowl. Okay, so if you take any circular bowl or elliptic bowl, okay, so which direction you will see the most rapid change, and which direction you will go with the uh, means increase or decrease, or there is no change. So when you go round off, means round is okay, you just put the finger and you just make a round, okay, along this circular. So you will not notice any change. Okay, it's all are similar. And when you go from downward to upward, you will see it's increasing most rapidly. And when you go from upward to downward, you are noticing that it's downward, means it's decreasing most rapidly. Okay, you will see. And what are the direction? Those is going to be, can be identified by finding the grade f. Okay, so this is what we can give it one uh, real life example of directional derivative, and where you will see the maximal change in the direction of grade f that you can actually identify when you know the equation of this circle. Okay, so as noticed, and you will not see any change if you take any direction which is orthogonal to grade f. So your f is given to you. Okay, so f of x comma y is something x square plus y square by 2. So it will increase most rapidly in the direction of grade f. So the grade f you can identify, that's going to be xi plus yj, if you recall. Okay, the first the ith component, that this I component is the partial derivative of f with respect to x. J component is the partial derivative of f with respect to y. Okay, if you have function of three variables, so you have one k component, and so in that you have a coefficient, you can find out that f partial derivative with respect to z. Now you are supposed to identify the change at the point 1 comma 1. Okay, so what will be, it's going to be is so grade f direction is nothing but at 1, comma 1, you can identify that's going to be x equals to 1 and y equals to 1. So this is going to be I plus j. This is going to be the direction where you will see most rapid increase in f. Okay, so this it's a violet color. Okay, tends it symbolize the grade f direction, and its blue color symbolize the direction of minus grade f. So you have the most rapid decrease when you have minus grade f in the direction of 1, comma 1. So it's going to be minus I minus j. Now, how to identify a vector? So again, as because we are in directional derivative, if you noticed that du, okay, f, so where u is a unit vector, so you have to find a unit vector. So you can find a unit vector, okay, so you can divide it by magnitude, okay, but still the value the direction will be the same, okay, it's only constant multiple. Okay, so now you will see no change when you have a direction which is orthogonal to grade f. Okay, so it is easy to identify now. So you have the for the first case, most rapid increase at 1, comma 1 will be in the direction is u equals to grade f divided by mod grade f. Okay, so that's going to be I plus j divided by square root of 2. Similarly, you have the answer for the most rapid decrease. Most rapid decrease at 1, comma 1 is going to be, so this all here is at the point. So you have to take, this is a p naught. Okay, at p naught. Okay, so everything is evaluated at the point p naught here. Okay, so keep in that point. So u equals to minus grade f, that mod grade f, that's going to be minus I plus j by square root of 2, just negative of grade f. And I hope you are comfortable in finding the magnitude of a vector. Okay, now what you will notice, so third, no change. For no change, you need to identify a vector, unit vector you can say, is orthogonal to grade f. At point, obviously at point p naught. Okay, so what is the definition of grade f? If you recall, is at p naught, you know, grade f at p naught is equals to I plus j. So the vector which is perpendicular to grade f is, you can identify any vector, okay, any vector which is orthogonal to this. So I minus j, you see the dot product of this with this is going to be 0. Okay, so you have this u unit vector is, can say it's going to be I minus j by square root of 2. So any scalar multiple of this will also work. Okay, so 1, comma 1, you can also identify geometrically. It's a, you can see this point will lie on the line y equals to x. So you are, what is the orthogonal? One is y equals to minus x. Okay, which makes an angle. Okay, right. And so we are done here. So no change in the direction which is orthogonal to grade f at p. Okay, right. Now let's so we have already identified the gradient. Okay, now let's first identify what is the meaning of this level curves. Okay, so what do we mean by level curve is as follows. Okay, so since you may have function of two variables, Okay, you may have function of 3 variables x, y, comma, z. You may have 4 more variables. Okay, so in the case of this variable, you have a equation of surface. Okay, so if you so it's a x comma y, this over which the domain will be there, okay, of f of x comma y, and you will have some surface on the z plane. So z equals to f of x comma y you are taking. Here you can take t equals to f of x comma y comma z, and so on, and define what is the dependent variable and what are the independent variables. So this direction obviously I'm talking about in this, so it is going to be this. Now, if you fix z equals to c, okay, z equals to c means you are having a line z equals to c. So it will cut the surface on a curve. Okay, that curve is known as the level. Okay, so it may have any type of shape. So similar for other more than 2 variables, 3 variables, and so on. So if you cut the surface by the line z equals to c, okay, so means you are substituting the surface, means you are trying to identify the point in the domain over which f of xy equals to a fixed constant c. Okay, once you do that, that will identify a curve in the surface. Okay, that will identify a curve here. Okay, that will be known as a level curves. Okay, right. Now, what is the definition of gradient? Okay, so this level curve, most of the time when you are cutting with the line z equals to c, okay, so these level curves most of the time are smooth. Okay, what do you mean by, what do you understand by smooth curve? Means it is at least differentiable. Okay, you will get a differentiable curve. Okay, so when you have the level curve, okay, so definitely you will have a projection on the xy plane. You will know what are the corresponding points that can be identified. Okay, so let's say that curve is going to be r of t is given by g of ti plus some h of tj, and I'm talking I may talk in the 3 dimension as well, so similar. Okay, let's say k of, or not k, let's because k is a component, so now you can have this n of t. Okay, okay. This is a c curve, that's a smooth curve. Okay, means this is a differentiable. Okay, so that curve I'm talking about, which is giving you over which you have the level curve. So any point on the level curve it can be obtained by, you can replace x by g of t, y by h of t, z by n of t equals to c. Now you can differentiate, because see, we are assuming that this f is a differentiable. When you're talking about the gradient, means we are assuming that, okay, we are assuming that first head is f is differentiable. Okay, we are assuming f is differentiable here. So apply the chain rule. Okay, so what it gives you, which we have already done, so that also you can verify that it is going to be grade f dot product. We have done this exercise in case of directional derivative. Grade f dot, you have dr by dt is equals to 0 when you differentiate with respect to t. Okay, so that is df by dt. You are trying to identify the df by dt. Okay, so if you are interested in the change or in f, okay, along that curve. Okay, so with respect to time, so what it tells you, so dr by dt, which we are named as velocity vector. Okay, so dr by dt is a velocity vector. Okay, which is going to be, you have, this is the component are g dash. It's very easy to identify, h dash of t, n dash of t, and so on. So it's very well confirmed from here that we are assuming that the curve C is smooth, means we are assuming that this G, H, and N are differentiable. So what is dr by dt on the level curve? They are nothing but the tangent. Okay, so velocity vector means this is velocity vector. So you have the tangent. Okay, and what it tells you at any point you are talking about. Okay, at any point, let's say p naught, x naught, comma y naught. Okay, anywhere you have the tangent dr by dt at p naught. So this the tangent will be given by dr by dt at p naught. And what you have just noticed that the gradient is going to be the perpendicular to the or orthogonal to that tangent. Means that it tells you that gradient f is normal to that curve. Okay, so this is why you will see most of the time that you have the definition in, or somewhere you will always say gradient f will be the normal to the surface and so on. Okay, so it attached with this normal name as well. So what it gives you is that grade f is going to be orthogonal to the velocity vector, and that will tell you that grade f is normal to this. Okay, right. Okay, right. So so this observation which is noticed here, okay, that tells you that at every point x naught, y naught, just now we have explained that this is the this is the level curve, and you have the at every point x naught, y naught in the domain of a differentiable function f, the gradient of f is normal to the level curve through x naught, y naught. Right? So gradient f is nothing but the orthogonal to that tangent vector that will give you the normal direction. Now, not only that, it will also help you to identify the tangent line passing through x naught, y naught, means at the point x naught, y naught. So if you take, so in the tangent line, what is there is, you take any point here. So this x naught, y naught is one point is there, and any point is, let's say, x comma y. Okay, so you can name this is a p naught, and you have this is a p1. Okay, so what this p naught p1 vector is going to be x minus x naught and y minus y, right? So but it is, you have noticed that this grade f is at p naught is orthogonal to this p naught p1, this vector. Just now we have just established that result. And now what is grade f at p naught is nothing but fx at p naught, means like x naught comma y naught, and another coefficient, another coordinate is fy at x naught y naught is orthogonal to this x minus x naught comma y minus y. Okay, this vector. So means their dot product will be 0. Okay, so hence this implies the equation of tangent. This implies you have fx at x naught comma y naught time x minus x naught plus fy at x naught comma y naught time y minus y naught is equals to 0. So you can identify the equation of tangent line. Okay, right. Now let's take one example here. Find an equation for the tangent to the ellipse. The given equation of ellipse is this, which you can easily draw. Okay, so x square by 4 plus y square equals to 2. So you can divide here, x square by 8 plus y square by 2 equals to 1. At the point minus 2 comma 1, and it is easy to verify that this point is lies in the ellipse. Okay, so just now you have learned what will be the tangent line. So you have so it's given, you are given with We are given with f of x comma y is equals to x square by 4 plus y square minus 2. Okay, you have been given with the point p naught, that is minus 2 comma 1. You are interested in finding a tangent line, okay, passing through p naught, okay, at p naught. So that's so tangent line at p naught will be what? This is going to be fx at p naught time x minus x naught plus fy at p naught time y minus y naught equals to 0. Right? So you have, so x naught, what is x naught? From here, so you can easily identify x naught is minus 2, y naught is 1, p naught is, fx is equals to, is going to be x by 4, so x by 2, and fy is equals to 2y. So fx at p naught, that is going to be x equals to minus 2, x and y equals to 1. So this is going to be minus 1, and fy at p naught is equals to 2. So you have all the information now. So you can substitute in 1. So 1 will imply that fx at p naught is minus 1. So minus 1 time x minus x naught, that is minus 2, right? Plus fy at p naught is 2, plus 2 time y minus y naught, that is 1, equals to 0. Now you can write this equation. Okay, so you are having minus time x plus 2 plus 2y minus 2 equals to 0. And this implies 2y minus x minus 4 equals to 0. So this is the equation of line, okay, which you can verify that this is going to be. So you can find out dy by dx is nothing but here minus 2. Oh, sorry, minus 1 by 2. Okay, and this, right? So you have all the information. So I think grade f at minus 2, 1 is, yes, right, minus I plus 2j. So do you have any question? Okay, fine. So you will see this gradient will behave like a differentiation function. Okay, differentiation, what you have learned, derivative, like a derivative. So this is this all four will tell you. So gradient of constant multiple of function, you can take constant outside and take the gradient. Similar like differentiability. Great. It is a linear, okay, with respect to addition and subtraction. So grade of f plus g is grade f plus grade g. Grade of f minus g is grade f minus grade g. Product rule also is valid. So grade of fg is equals to, you can take f grade g plus g times grade f. So first function as it is, derivative of second function as it is, plus derivative of first function. Similar about the quotient rule. Okay, so grade of f by g, this is going to be g square, g times grade f minus f. So it is easy to verify, okay, all these things. So I'm not going to I'm not going with any example for verifying these properties. That you can do at your own. You can take a function of two variable, okay, and try to verify. Okay, that you can do that. Right. So as already mentioned, that you can extend now all the defined definition, okay, in the case of 3 variable or 4 variable and so on. as follows. So for a differentiable function f and unit vector u in space, we have grade f as told. You have additional this third term, that is k component with coefficient is f with respect to z, partial derivative. And the directional derivative, again, now it's easy to generalize. Okay, if you are still with that limiting definition, that is somewhere, okay, you have one more argument will come, x naught plus su1 comma y naught plus su2 comma z naught plus su3 minus f of x naught comma y naught comma z naught divided by s, and limit s tends to 0. But here now the life is easy because you have to only identify the grade f at the point p naught and take the dot product with you. Okay, so similar, you can extend now 4 variable, 5 variable, and so on. Okay, now again, so grade f, what it tells you, okay, again, is it will also give you tangent plane and normal lines. So how? Okay, so let me try to say. So you have the level curves again, f of x comma y comma z equals to c. Okay, again you will again move forward for so again we have the same assumption that it will have the curve is smooth. So I think we have already done for the 3 variables, right, just now. Okay, so what we observe is at point p naught, that is easy to verify, p naught at x naught comma y naught comma z naught, it is easy to verify that grade f is at p naught is going to be orthogonal to dr by dt. That's a vector at p. So this will give you again with the similar, so perpendicular to this orthogonal dr by dt. Okay, so that will give you, so that dot product. Okay, so this will tell you that on the tangent line, you take any point. Okay, so means you have, this is fx at p naught comma fy at p naught comma fz at p naught. This vector is orthogonal to any vector which is passing through this tangent line and which is going to be x minus x naught comma y minus y naught comma z minus z. Right? Okay, so now this implies, means this dot product is 0. So this implies you have this fx at p naught times x minus x naught plus fy at p naught times y minus y naught plus fz at p naught times z minus z naught equals to 0. Substitute everything here. That will give you, so that gives equation of tangent plane. Equation of tangent plane. Now, to identify the equation of normal line, what you have to see? So you have to look at the vector which is orthogonal to this velocity vector or tangent line. That will give you the normal. Okay. In other words, any vector which is parallel to the normal. Okay, this grade f at p naught will give you the normal line. Okay, so for the normal line, okay, for normal line, okay, you choose a vector, so grade f at p naught, which is parallel to the line x minus x naught comma y minus y naught comma z minus z. Any line which parallel to this. Okay, this direction. So what it means, you have the equation of normal line x minus x naught divided by fx at p naught. is equals to y minus y naught divided by fy at p naught plus z equals to z minus z naught divided by fz at p. So these will give you the equation of normal line. So this is known as equation of normal. Okay, which will be equation of normal line. Okay, right. So any line which is parallel to the gradient f will give you the normal line. Any plane, okay, or any line which is going to be, you can generate a plane. Okay, any vector which is means perpendicular to this means you have to look at the plane where. So in other words, you are here. What you are doing? You are trying to on the surface. Means you have a surface, okay, and you have a plane, and which is you have on the domain, you have somewhere x naught comma y naught comma z naught. Okay, so means you have a point here x here p naught is x naught comma y naught comma z naught, and you identify any point here x comma y comma z. Okay, so here is x naught comma y naught in the domain. Okay, so x naught comma y naught comma z naught, you are trying to identify the equation of tangent plane. So on the tangent plane, what you can identify is going to be what we just now verified is grade f is going to be the normal at p naught. So so you take any vector on this tangent plane, it still will be a normal. You can move any direction on this plane, rectangular plane, you can say. So grade f means you can look at by example, means you can say you can take any rectangular plate in your hand. You can identify a point P naught there. Okay, and you can just make your pencil vertical. Okay, that will be the grade f to that point. But if you move anywhere on that plate, it will still be a normal. Okay, so that rectangular plate will be can be identified as a tangent plane. Okay, I hope that is clear now. Okay, so we have both now equation of tangent plane and equation of normal line. Okay, so these are the definitions. I think it's readable now. So the tangent plane at the point is on the level surface of a differentiable function f is nothing but the plane through p naught normal to grade f at p. So just now we have just shown this. And the normal line of the surface at the point P naught is nothing but the line through P naught which is parallel to the grade f. Okay, right. So we have the equation of tangent plane and normal line. So let's try to work out with an example. Okay, so I will do the first example. Okay, second example we will leave it as for our tutorial. Okay, so the first example says that find the tangent plane and normal line of the surface is at the point 1 comma 2 comma 4. Okay, so example 1 I'm just solving. So we have been given with f of x comma y comma z equals to x square plus y square plus z minus 9. X square plus y square plus z minus 9. Right? And you are trying to identify at the point P is 1 to 4. That's P naught, 1 comma 2 comma 4. So equation of tangent plane or equation of normal line. Okay, in both the cases, we need to identify grade f at P naught. So for tangent plane at normal line. Okay. We first find grade f at P naught. Okay. So you have the definition of f. So now it is easy that now you have f of f is equals to x square plus y square plus z minus 9. Okay. So what is grade f here is nothing but I'm just again writing fxi plus fyj plus fzk so that it will be clear to all. So fx means partial derivative of f with respect to x, that is 2x I. Fy, partial derivative of f with respect to y, that is 2y. Fz is f partial derivative with respect to z, that is 1. So that's k. Now, grade f at p naught. So p naught is 1, 2, 4. So that is going to be x equals to 1, y equals to 2, and z equals to 4. So that's going to be 2i plus 4j plus k. So that's going to be the normal to the surface, grade f. Okay. Now, now the equation of tangent plane passing through P naught, that is 1, 2, 4, x naught, y naught, z naught, will be fx at P naught time x minus x naught, that is 1, plus fy at P naught time y minus y naught, that is 2, plus fz at P naught times z minus z naught, that is 4, that's equals to 0. Okay. So fx at P naught, fy at P naught, and fz at P naught, just now you have identified. Okay. They are nothing but the component of the grade f, right? They are nothing but the component of grade f. So just now we have identified that. Let's look at it. So just now you have identified that from here you can also, this implies fx at P naught equals to 2, fy at P naught equals to 4, fz at P naught equals to 1. Okay. Now I have to write. So the equation of tangent plane passing through P naught 1, 2, 4 will be fx at P naught times x minus 1 plus fy at P naught y minus 2 plus fz at P naught z minus 4 equals to 0. And fx at P naught, just now we have identified that is 2, 4, 1 now. Okay, so 2 times x minus 1 plus 4 times y minus 2 plus z minus 4 equals to 0. And you can rewrite this 2x plus 4y plus z minus 2 minus 4 minus 6 and minus 8 is minus 14. So that's equals to 4. So this will be the equation of tangent plane, okay, passing through the point 1, 2, 4. Okay. Right. So now similarly you can identify the equation of normal line. Okay. So the equation of normal line through P naught will be x minus x naught, that is 1, divided by fx at P naught. Okay, let me write it. Fx at P naught is equals to y minus y naught, that is 2, divided by fy at P naught, and that is equals to z minus z naught divided by fz at P naught. And all these values, fx at P naught is 2, fy at P naught is 4, fz at P naught is 1. So this implies x minus 1 by 2 equals to y minus 2 by 4 equals to z minus 4 by 2. Okay, now you can easily you can identify equals to some arc length parameter. You can take t or s, that will give you the equation of line. Okay, so second example you have to you can do, okay, or we will see during the tutorial class. Okay, now so I hope this thing is very much aware of among you. Okay, change in f. Okay, forget about right now in a direction. So for a function of single variable f, if you want to identify change in f, okay, with respect to x, in that means, okay, with respect to x, what it will be, df at point x naught is nothing but f dash at x naught time dx, if you recall. That will give you the change in f, okay, when we are with respect to x time f dash of x naught will give you the change in f. Now, since you have already encountered it now with the definition of directional derivative, okay, so this derivative now, when you talk about function of more variables now, 2 or 3 or and so on, okay, you can replace this by directional derivative, and which can be further replaced by this dot product. Okay, so grade f at P naught time dot u and ds, s is nothing but the arc length parameter again, okay, of the curve. So we can now read this, the change in the value of a differentiable function f. Of course, we require the differentiability. When we move a small distance ds from a point P naught in a particular direction u. So u is here again unit vector. Okay, we are talking about in the unit vector because we are talking about the directional derivative. So will be given by the following formula. So that formula is now easy to memorize once you know this. Okay, so this f dash of x naught is replaced by the directional derivative at P naught in the direction of u. Now it is easy to handle this example now. Estimate how much the value of f will change if the point moves 0.1 unit from the point P naught straight toward to P. Okay. Okay. So how will you do that? This problem. So you have been given with you are trying to identify the change in f. So f is given by y times sine x plus 2yz. Okay. So what is the vector? So you need to identify in the direction. So what is the direction is P naught to P1. We are moving from P naught to P1. Straight forward. Okay, straight toward this. So P naught is 0, 1, 0. And P1 is 2, 2, minus 2. So what is U? Is nothing but P naught P1 divided by mod of P naught P1. Unit factor. Okay, so this is going to be, you have this is 2i plus j minus 2k divided by, so this is square root of 2 square plus 2 square, that's 4 plus 4 is 8 plus 1 9, that's going to be 3. 9 square root is 3. So unit vector, you are trying to identify unit vector in the direction of this. Okay, now you need to identify grade f at P naught, because you are moving from P naught to P1 with the TS unit. So grade f at P naught is nothing but fx at P naught, fy at P naught, fz at P naught. So you can identify from the definition f that what is fx. So what is fx is y time cos x. What is fy is sin x plus 2z. What is fz is 2y. Now fx at P naught, what is P naught? P naught is 0, 1, 0. So x is 0, y is 1, and z is 0. So x is 0, cos 0 is 1, y is 1. So fx at P naught is 1. Fy at P naught, sin 0 is 0. 2 times 0 is also 0, is 0. Fz at P naught is going to be 2. So this implies grade f at P naught is equals to I plus 2k. There is no component for j. Right? So what is duf now? At P naught is going to be grade f at P naught dot product with u. Okay, so what it will be? So grade f is I plus 2k dot product with u. Sorry, u is 2i plus j minus 2k divided by 3. Now you can take this dot product here. So this implies, so directional derivative of u in f in the direction of u at P naught is equals to, okay, so 1 by 3 that's out. So you have 2 minus 4, right? So 2 minus 4. So that is going to be minus 2 by 3. So we know that df is nothing but duf at P naught in the ds. So that's going to be minus 2 by 3 into ds was 0.1 unit is mentioned. So it's going to be something like minus 0.2 by 3. So it's going to be minus 0.06666 approximately. Okay, so there's a negative change. Okay, so right. Okay, now if you have any doubt, you just let me know. Okay, or else we will move forward. Okay, let's move forward now. So now we are going to introduce a new method, which is named as method of Lagrange multipliers, which essentially are extremely useful, okay, in finding the extreme values, okay, in finding the extreme values of a function f of x comma y comma z, okay, whose variables x, y, z are subject to a constraint, okay, subject to a constraint G some it should satisfy some of the equation G of x comma y comma z equals to 0. Sometime what people do is they will treat z as a dependent variable, x and y are independent variable. From here they will express z in terms of x and y, replace it here and make it function of two variables and try to use first derivative test and second derivative test and so on. But it will not work all the time. Okay, so this we will try to understand that substitution will not work all the time, okay, so smoothly than you expecting. Okay, so let's try to work out one example. So you will see that, okay, you will analyze that how the substitution will not work. So we are interested, let's look at this example. We try to identify the point P which is closest to the origin on the following plane. So you are trying to identify a point P on the plane which is closest to the origin. Okay, so you know, if you have P, you know what if you take any point P on the plane, what is the equation of you can have that what is the shorter distance formula is square root of x square plus y square plus z. Okay, so what we are trying to identify is we wish to find the minimum value of this function. Okay, that's going to be square root of x square plus y square plus z. We try to identify the minimum value of this. Subject, so here x, y, and z are not belonging to entire space. If it is an entire space, then you can work out with other things. Okay, but they are subject to, so x, y, z are such that here, such that 2x plus y minus z minus 5 equals to 0. So they satisfy the equation of this tangent. Not tangent on this plane. Okay. Now, without loss of generality, I can assume that instead of working with this square root, I can straightforward work with this x square plus y square plus z. Okay, later on I will put the square root because minimization of this square root function, okay, immediately implies the minimization of this argument. Okay, so to we don't want to make the things too complex. So we can, in particular, we can work on the function f of x comma, we can minimize this function f of x comma y comma z, that's equals to x square plus y square plus z square, subject to the constraint, subject to the constraint 2x plus y minus z minus 5 equals to 0. So we want to find minimum value of f of this. Now, as I mentioned, we can also, so let's let x and y be independent variables. Okay, let x and y be independent variable. So let's say this is 1 and this is 2. Okay, so from 2, what you have, z equals to 2x plus y minus 5. And therefore, you have, 1 implies f of x comma y comma z. What is z is 2x plus y minus 5 is equals to x square plus y square plus z square. So that is 2x plus y minus 5 whole square. Now it involves a function of two variables, and which we denote, let's denote it by some function h of x comma y. Okay, so let's assume this is a function of two variables, that is h of x comma y. Now you can work out with first derivative test and second derivative test and so on. This function is nice. You have positive powers and everything is nice. You have all the first order, second order partial derivative exists and continues and so on. Later on, we will see whether the obtained point will lie on the plane or not. Okay. So first we try to identify the nature or identify the extreme points, critical points. Okay. So for critical points, hx equals to 0 and hy equals to 0. Rather simplifying it, you can straightforward work with it. Okay. So now this implies, so hx, what is hx? So hx is first order partial derivative with respect to x, so 2x plus, so 2x plus 2 times 2x plus y minus 5 times, right? Derivative of this 2 times this, and then coefficient of x, that is going to be 2, is equals to 0. And if you differentiate partially with respect to y, is 2y plus similarly 2 times 2x plus y minus 5 times y coefficient, that is 1 equals to 0. And these two together, okay, solve out. Okay, so 2x plus 2 into 2, 4 into 2 is 8. 8 plus 2 is 10x. Okay, plus 4y minus 20 equals to 0, so equals to 20. The first equation is this. Second equation is 4x. This is plus 2y is plus 4y. This is minus 10, so it's equal to 10. Now, solve these two equations. So it's very easy. So this will cancel. So you have 6x equals to 10. So implies x equals to 10 by 6, and that is going to be 5 by 3. Okay. And now from here, you can find out that x equals to, x is already obtained. So y equals to 10 minus 4x divided by 4. Okay, so that's going to be, you have minus 4x. Okay, so it's 20 by 3. So 30 minus 20 is 10, right? So 10 by 3 into 4 is 12. So it's going to be 5 by 6. So you obtain the following points. So x equals to 5 by 3 and y equals to 5 by 6. So z coordinate, how will you obtain? Because you have obtained the two coordinates, x equals to 5 by 3 and y equals to 5 by 6. So z coordinate, you know that z equals to 2x plus y minus 5. Should satisfy the equation, right? So from here, you can identify the z coordinate. So z equals to 2 times 5 by 3 plus 5 by 6 minus 5. So it's going to be 10 by 3 plus 5 by 6 minus 5. So that is going to be turn out to be, so it's going to be, so 25 by 6 minus 5. So it's going to be minus 5 by 6. So you have the coordinates now. So P is a point. So X is 5 by 3, Y is 5 by 6, and Z is minus 5 by 6. Certainly it lies on that XY, that plane, equation of plane, 2x plus y minus z minus 5 equals to 0. Okay, that will satisfy that. Moreover, you can also verify hxx is equals to what? What is hxx? Is nothing but 10. What is hyy is 4. Okay. So hxx is 10. Hyy is 4. Hxy is equals to is 4. So we can certainly have hxx in to 40 minus 4 square is 16, that is greater than 0. And hxx is also greater than 0. So this will identify, second derivative test tells you that it is minimum. Okay, at that point. Okay, so what it will do, so it will locate the closest point. The substitution method worked nicely here. Okay, right. Now, so now finally you can, it's like you can certainly find out now mod of OP. Okay, so that you can identify. Okay, that's going to be square root of, okay, x minus square root of x square plus y square plus z square. So it's going to be this square plus this square plus this square. Then take the square root, that we can identify certainly. Now let's look at another example. Okay. Okay, so let's look at another example. Find points closest to the origin on the hyperbolic cylinder. Okay, on the following hyperbolic cylinder. How will you do that? Is again, you may have followed the same approach what we have just now followed. Okay, so what it will do? Okay, so we are trying to identify that again by the similar logic. We can say we are trying to identify minimum value of f of x comma y comma z is equals to x square plus y square plus z square, subject to the constraint, subject to the constraints, subject to the constraint. Okay, x square minus z square equals to 1, or minus 1 equals to 0. Okay, right. Now again, what you can do, okay, so from here, certainly let, again you will opt with the same thing. So let x comma y are independent, be independent. Okay, then you have z square equals to, it's like from here equation of cylinder. Okay, the cylinder, so this you can have, this is 1, this is 2. So from 2 what you will have is z square equals to x square minus 1. Okay, so from that you can express z in terms of this. So therefore what is f of x comma y comma z? Z is nothing but plus minus square root of x square minus 1, right? So that's going to be x square plus y square plus z square. In any case, it's going to be plus x square minus 1. So that's going to be 2x square plus y square minus 1. Now, again, let h of x comma y is equals to 2x square plus y square minus 1. Now here you will repeat the same process, means for extreme points or for critical points, you need hx equals to 0 and hy equals to 0. So for critical points, hx equals to 0 and hy equals to 0. But if you take hx, what is hx is 4x. What is hy is 2y. Okay. So this will give you, this implies 4x equals to 0 and 2y equals to 0. And which leads to the only possible critical point is 0, 0. Right? So, but if you look at the shape of the cylinder, okay, this hyperbolic cylinder, which is here, okay. So this cylinder is neither, I mean, it will never cross this origin, okay, 0, 0 point. Okay, no point will lie on, I mean, this 0, 0 point will never will be coming into the picture. So we are wrong somewhere. Means this method will not work. Okay, so how? So first question is, how will you generate this cylinder? Is okay. So you just draw a hyperbolic curve. Okay, passing through in the plane x comma z. Okay, and stretch it along the y-axis. Okay, so you stretch it along the y-axis, means y is the perpendicular to x and z space. Okay, so draw a hyperbolic curve. So this is a hyperbolic curve. Okay, you have this x equals to square root of z square plus 1, and then stretch it along a y direction. So it's a y direction. So you are stretching along. So this will generate, okay, the hyperbolic cylinder. Okay, so but the point is here is it will never cut the origin. 0, 0 point will never be here. Okay, so now let's choose another way. Okay, where will come the original method later. Okay, now let's regard this. Okay, now let us assume that y and z are independent. Okay, be independent. Let y and z be independent. Sorry. Okay, so let y and z be independent. So so then what you will have, x square minus z square equals to 1 implies x square equals to 1 plus z square. Now, and what is f? F is equals to x square is 1 plus z square plus y square plus z square. So that's going to be 5 square plus 2z square plus 1. And which you let this is denoted by k of y comma z. Now again, for possible critical points, what you can say is ky equals to 0 and kz equals to 0. Now this implies certainly ky is 2y, kz is 4z. So this will implies 0. Ky is 2y equals to 0 and kz equals to 0 is 4z equals to 0. So this again implied point 0 comma 0 on the yz. Okay, in the yz will be the possible critical. And so what are the points you look? Okay, so again, if you look back in the geometry, okay, so this will be, okay, this is x equals to 1 here, this x equals to minus 1. Okay, so if you look at the geometry, it will be, means the closest point is nothing but here. Okay, if you look at the geometry. Okay, so from here it can be seen, so y comma z equals to 0 and x square equals to 1 plus z square, that is equals to 1. This implies, which is x equals to plus minus 1. So the possible points, okay, possible points are of the form x comma 0 comma 0. Only possible points are there. Now, what are the points are 1 comma 0 0 and minus 1 comma 0 comma 0. both will point of extrema. Okay, now you can further find out, okay, that this will give you the minimum value. Okay, so again use the second derivative test, that kyy is equals to 2, kzz is equals to 4, kyz is 0. Okay, that you can easily identify. So kyy is, so ky is 2y. So again you differentiate with respect to y2, and you differentiate with respect to z, that is 0. Similar kzz, you will get 4. Okay, so this will tell you, this implies you have what you have, kyy times kzz minus kyz whole square is greater than 0, and kyy is greater than 0. So it will attain a minimum value, okay, at 0 point. Now, so then you have, you can obtain certainly the minimum value now, okay, plus or minus 1, okay, 1 comma 0 comma 0. So f minimum value is nothing but plus minus 1 comma 0 comma 0 is nothing but the unit distance, right? Anyway you look for. So square root of 1 is also 1. Now let's try to, okay, so so we have time up. Okay, so what we will do in next is we will try to define now the method of Lagrange multiplier. Okay, and then we will see that now means you no need to worry which way you will decide the, or what are the variables you can choose as independent. And okay, so because here y and z, if you take as dependent variable or independent variable, then the method works, substitution method. But whereas if you choose x and y as independent, then it will not work. Okay, because you have to have some insight in the geometry as well. Okay, right, so we end here. Okay, if you have any doubt, we can discuss, okay? Or else we can leave.
Sir,
Yes,
so can we use tangent and normal for finding this point? Like,
we are coming to that.
okay,
Method of Lagrange multiplier will only lead that.
like you finding the
You will see soon that which you are optimizing. Okay, like f is your optimizing subject to the constraint is g. Okay, so g is a surface, g of x comma y comma z, and f. You will see that method of Lagrange multiplier will tell you the normal to the surface, both the surface will be parallel. Okay, that you will soon realize in the next meeting. Of course,
Thank
you're
you, sir.
right. Okay, thank you.
Thank you, sir.
Thank you.